second lecture this morning is the course of Francisco Urbano. He is going to talk about the stability of minimal surface.
Okay, good morning. As you remember, yesterday we were proving that characterization of the stability given by Fisher, Covey, and Sean in the 80s. And this theorem had two important corollaries. The second one is quite important in the sense that it proved that any minimal graph is automatically stable. Well, as I said yesterday, they proved the result in a more general context. So let me give the theorem that Fisher, Covey, and Sean proved. They consider any Riemannian manifold and any Schrödinger operator. Q has no any restriction. And then the operator L is stable if and only if there exists a positive Jacobi function. Okay? This means that a positive function is in the kernel of the operator. For the sufficient condition, it's not necessary the non-compassive. It's true for any many. But for the necessary condition is necessary. You have to assume that the manifold is non-compassive. Okay? Well, then yesterday we proved the sufficient condition, and in the necessary condition we proved the following. If you assume that the operator is stable, then for any relatively compact open subset, the first eigenvalue of the Schrödinger operator on omega is positive. Okay? If the operator is stable, then the first eigenvalue is non-negative. And we prove that it's impossible that the first eigenvalue is equal to 0. So we prove this. Well, we continue with the proof, and today we are going to see the following. We take any relatively compact open subset of omega, and then on omega, and if we fix a point P in omega, we are going to construct a positive function in the kernel of the Jacobi operator, and which have we take the values 1 as me. 1 is not correct. Any positive. Okay. Well, how we can prove that? We are going to use again section 3 in the notes. So we are going to use some classical results. So I consider the following Dirichlet problem. In the domain omega. L of f equal to 0 and f equal to 0 on the boundary. Okay, I consider it Dirichlet problem. Then the solution, the only solution is f equal to 0. Because if you find a non-trivial function satisfying this equation, the first eigenvalue vanishes. Okay. Now, as the only solution to this Dirichlet problem is the trivial solution, I can use the Frekhum alternative that you can find there. Then I use the Frekhum alternative. Then, if I consider this problem, LP equal to minus Q. Q is the potential of the Schrödinger operator, and V equal to 0 of the boundary. Then this one has a unique solution. Okay? So we have found a function which satisfies this equation omega and is 0 on the boundary. Okay? Now we define tilde p like p plus 1. Okay? and we study this function here. We have the Rodinger operator acting on P tilde is equal to L applied to E minus Q plus the Rodinger operator acting on 1. The Rodinger operator is the sum of the Laplacian of Q. So we get this. And this means that this is equal to 0. Okay? In omega. And V tilde is equal to 1 on the boundary. Okay? So we have found a function which is in the kernel of the Rodinger operator, and in the boundary is equal to 1. Okay? We are going to see that this function is positive. Right. We want to see that this function is positive in the domain. Okay. Well, to do that, I take omega naught, the set of points in omega, where this function is. Okay, this is an open subset, included, in omega. Okay, and this one is relatively compact again. Now, the function P tilde satisfies that the Rodinger operator over P tilde is equal to 0 in omega naught, because it's true of omega. Okay, and of course, P tilde and the boundary of omega 0 is C. Okay? But again, using the same argument at the beginning, this function P tilde is equal to is equal to 0. Okay? And this is impossible. So omega naught is equal to empty set. So our function P tilde is bigger than or equal to C. There are no points where the function is negative. Okay? Well, suppose, but in that case, you take omega, P tilde is in the kernel of the Schrödinger operator, and P tilde is bigger than or equal to 0. Then you use the maximum principle that you can find, or a consequence of the maximum principle that you can find in the nodes, and you get that P tilde is positive or P tilde is 0. P tilde 0 is impossible because it's equal to 1 the boundary, so P tilde is equal. So, okay, P tilde is positive. Okay, because it's impossible. So we have proved that P tilde is positive. And now the function U that I need to define is given by this one. U of x is equal to P tilde in the point x over P tilde. Point P. P is the point that I have fished here. Okay. Then this function is a constant time. P tilde satisfying the same equation. This is L U is equal to 0. U is positive because P tilde is positive, and U at P naught. P, sorry, is equal to 1. Okay. This is the way in which we prove this result here. Okay? Not complicated, but we have using some classical machinery in this kind of arguments. Well, now we have to extend in some sense the function u to the whole manifold. Okay, this is the only question. So to do that, we are going to use the Harnack inequality to prove that. Then I consider a sequence of relative compact open subsets of the manifold, okay, in such a way that the project of n omega n is included in the next one, for any n, at the union in n of this open domain is the manifold. Okay. And now I fix a point P in all the omega n. Consider a point P in omega n for any n. No problem, because I take a point in the first one. And use the result for each omega n. Then you have a function defined in omega n satisfy this three properties. Is in the kernel of the Jacobi operator, is positive, and in the point P is equal to 1. Okay? You can do to apply this one to all the set in the sequence. Then you get this. And now I take any relatively compact open domain which contain to the point P. This is not a restriction, because if it's not contained to the P, you can add another set that contains to the point P. Okay? And then, as the union of all these open subsets is equal to n, there exists an integer such that omega is included in omega n for n bigger than or equal to. Okay? And now I use to this couple of domain the Harnack inequality that you can find also in the notes. Then the sum of un applied to x with x in the smaller domain is less than or equal to a constant. The constant only depends of the domain. Okay? The inf figure of uns x in the smaller domain. This is the Harnack inequality. Okay? But all the function at the point P is equal to 1. Then this inferior is less than or equal to 1. Okay? Because there exists a point in omega in which the function un is equal to 1. So this number is less than or equal to c. Okay? So, what does it mean? It means that the function un are uniformly bounded on compact domain. Okay? And now we use classical result that you can find in their book. And then under this condition, a subsequent of un converges to a function all the way. And of course, the properties are the same, that is the property of un. Okay? This is more or less the proof, no more or less the proof of the result. And it's interesting because you can have, when you you have stability, you can have a function u. But this function u is nice because it's smooth, it's positive, and it's a Jacobi function, but you don't know how to define it. Okay? Well, now let's go to continue with the study of the hypersurfaces. Then the first thing that today we are going, the second thing that today we are going to see is that why people study this problem when the manifold is complete. Why it's important to assume the completeness of the hypersurface. So, la luz es importante. Well, why? Because when you take a hypersurface of Euclidean space, then given any point P, you can find a neighborhood around P in such a way that this neighborhood is graph. Okay? This is only to use the implicit function theory. Very easy. But we have seen before that all the graphs are stable. So what does it mean? It means that in any minimal hypersurface, even at any point, there is a little neighborhood which is stable. Okay? Then, how many possibilities we have to study this problem? In my opinion, 2. Or I consider complete hypersurfaces. It means that they are very, very big in some sense. Or you decided to study what happened with the stability, depending on the domain. If the domain is of this form, it's stable. If it's of this another shape, it's not stable. If it's very big, it's not stable. And there are many situations. It's not the way to study. So the natural problem is to consider to study complete stable minimal hypersurface. Okay? Well, now the only example that we have studied until now are the graph. Then let me relate the graph with the completeness. In order to do that, I'm going to define, everybody knows that an entire minimal graph is a graph defined on the whole Euclidean space of dimension n. This means that the function f which satisfies the equation of the graph is defined on all the Euclidean space. Well, if you remember, yesterday, when I introduced you the graph, you have the graph, sorry, defined in all Euclidean space, phi applied to a point x is equal to x. Okay, and f. The function which defines the graph. If you remember, the induced metric here by this immersion was given by the Euclidean metric there plus these two tensors, df. Okay. But this one is bigger than or equal to Euclidean metric. And the Euclidean metric on the whole Rn is complete. And this metric is bigger than this one, which is complete. G is also complete. Okay. So the entire minimal graph are automatically complete. The convert is true. There are complete graphs which are not entire. Okay. So the entire minimal graph are the first example of complete manifold, in particular the hyperplane. Well, let me now give a a proposition, a very easy proposition, in order to have in mind that when we obtain some stable minimal hypersurfaces in some dimension, you automatically have a sample of all the dimensions. That is very easy. I'm going to explain here. It happened with this in the case of stable minimal hypersurfaces and also in the entire minimal graph. So if you take such immersion, okay, you take the product of this map and the identity, where the identity is the identity in the Euclidean space. Okay. And then this is also an immersion, trivial. And if you compute the mean curvature here, you get that the mean curvature in this manifold at the point xy is equal to the mean curvature of the original one at the point x. Or you are taking the product. Okay? So this manifold is orientable, is complete, because it's the product of complete manifold, and is minimal. And also stable, using again the result of Fisher correlation, because if this one is stable, you have a function in the kernel of the Jacobi operator here, and which is positive. Okay? Then in this manifold, I define u tilde over xy like u over x. And this function is positive and is in the kernel of the Jacobi operator here. Okay? So with a stable minimal hypersurfaces you produce in all the higher dimensions, an example quite similar. Okay, this is important. And with the graph, it happened the same, because you have any graph, any entire minimal graph, okay, defined by a function f. The function which defines the entire minimal graph, then you consider the function similar to that one, f tilde over xy equal to f over x. Okay? And then this function satisfies here the equation of minimal graph and is entire, so you can produce graph in higher levels. It's a trivial way to produce them. You have to have in mind, you are classifying, you have to have in mind that in all the inferior less dimensions, you need to consider this as something. Okay? Bueno, Magdalena ya puede, porque ya no voy a escribir. Okay, so let's go to study entire minimal graph. We are going to dedicate the rest of the conference today to study the approaches that people made to the Bernstein problem in the 60s. Of course, in the next quiz, I will give a new proof. Okay, but today, for me, it's important that everybody more or less know how they proved the result 60 years ago. Okay, so I am going to dedicate. I'm not going to enter in detail because there are many theories behind the proof. But I would like that everybody has some idea of how they prove the result. Okay. And then the first thing that somebody that began to study entire minimal graph say, okay, I can produce many entire graph. How? I take a ball centered in the origin of an n and radius r, and I consider the following Euclidean problem. The equation of the graph and I suppose that, and I impose that the function is equal to any function on the boundary. It's enough to consider continuous function. If you want, you can take more regularity. It doesn't matter. And then you have a solution. Then you have a graph on the pole that, and in the boundary, the function is f in the boundary. So the problem is, well, I take r going to infinity, and I am choosing suitable function. And then one might expect that in this way you can get many entire minimal graphs, one or other. This was the surprise, the classical Pepton theorem that I talked yesterday, and he proved that it's not true, because if you make this method, at least in the plane, the only solution that you obtain is the polynomial degree. Okay, this is important. Well, then the Bernstein problem was extended to any dimension. Yesterday I talked about that, and here you can see that I have written here hypercone of Rn. Then the problem is that in the 60s, that people related the hypercone in the Euclidean space with the minimal graph in the Euclidean space. This was a very strange relation, but it was their idea. So let me explain a little bit what is a hypercone and how is the relationship between this theory of hypercone and the theory of stable minimal, entire minimal graph. Well, the hypercone that I am going to consider, I take the Euclidean space of dimension n. In here, I consider the unit sphere, and I take any hypersurface. I am assuming that n is compact, because the good examples are compact. Okay, any hypersurface of an orientable manifold. Okay, and then with phi, I construct a hypercone in this Euclidean space, the same dimension, which is defined on the cylinder over the manifold, and is defined in this classical way, meaning that you take here the sphere, you take here any minimal submanifold, then you take the origin and you consider this cone, okay, over the hypersurface. Well, of course, this cone has a singularity in the origin, except when the hypersurface n is an equation. In that case, it's a hyperplane which extends regularity nice way to the origin. So it's not difficult, this exercise, to relate the mean curvature of the cone and the mean curvature of this hypersurface of the sphere. Then the cone is minimal if and only if phi is minimal. Minimal in the sphere. Okay? This is it's very easy to see. And also, I need a definition that everybody knows here, which is when a minimal hypercone is volume minimized. Then they use this definition. A minimal hypercone is volume minimizing if you fix any r, any radius, and then the intersection of the cone with the volume of radius r is volume minimizing in the sense that its volume is less than or equal to the volume of another hypersurfaces with the same boundary. Okay? This is a classical definition. The volume minimizing hypercone, in particular, they are stable. Okay? Then with this definition, Fleming and De Giusti gave this nice and strange, but for me it's very nice. They proved the following. If the only volume minimizing minimal hypercone in the Euclidean space of dimension n are hyperplane. Then, in the Euclidean space of one dimension more, the only entire minimal graph are hyperplane. Don't ask me how they prove the result. It's very long, it's very long, many theories behind it. It's not equivalent to the two problems, okay? But they related the volume minimizing minimal hypercone of the Euclidean space of dimension n with the entire minimal graph of one dimension, okay? So this result opened the door to prove the Bernstein theorem. But then, not Bernstein, because Bernstein in 80s, he gave another proof, but the Georgi in 65 for n equal to 3, Algren in 66 for n equal to 4, and James Simon in his famous paper in 68 for n equal to 5, 6, and 7 prove that the only entire minimal graph are hyperplanes. Okay, how do they prove the result? But they prove that for n less than or equal to 7, the only stable minimal hypercone of the Euclidean space are hyperplanes. In particular, the volume minimized. Okay? All of them use the same theory. They prove the result. And it's difficult to prove that the only stable minimal hypercone are hyperplane. No, and I say you because here the cone depends on two variables: a real variable t and the variable in the sphere of the original immersion. Then Simon studied two different operators. One operator acting on real function and the Jacobi operator of the minimal hypersurface of the sphere. And then he proved that if there is some relationship between the two first eigenvalues of these two operators, then the hypercone is stable. It's not difficult to prove. Okay. Well, so in this way they solve almost, because they prove that for n less than or equal to 7, only there are hyperplanes. But the problem is what happened in higher dimensions. Then Simon discovered that when n is equal to 8, there are examples of hypercones which are volume minimizing, but they are not hypercones. Okay? This is the famous cone of James Simon. How to produce this cone? But in this way, you consider in the Euclidean space the 7-dimensional sphere, and you take there the Clifford dot. Okay, this is a minimal compact minimal hypersurface. It's very well known, and then the associated minimal hypercone in R8 is this nice hypersurface. Okay. Second point, I identify R4 times R4 with R8. And then it's easy to see that this hypercone is stable, and a little bit more difficult to prove that it's volume minimized. Then you don't use the Fleming result, okay? But although the Fleming and the Justin result is not an equivalent, it's natural to think that if in R8 there exists a hypercone volume minimizing, which is not a hyperplane, it's natural to think that in R9 there exists a stable entire minimal graph, which is not a hyperplane. And this was proved by the famous paper of Convieri, De Giorgi, Justin in 69, where they prove that in R9 they can construct a stable, an entire minimal graph. Okay. Let me explain a little bit how they prove the result. Of course, this is a paper in Invenciones Matemáticas with 40 pages. It's quite difficult. Anyway, there are people that have extended this result to another situation, and probably that paper are easier to read than this one. Well, let me explain how they produce the graph. In order to produce an entire minimal graph in R9, they need to get a function to find all R8, which is a solution of the classical equation. Okay, I will put here epsilon instead of to work with this operator. It's very long to write. Well, the first thing that they thought about was we would like to find solutions which are invariant under the axiom of the orthogonal group SU4 times SU4 over R4 times R4. Okay? This means that in really the function f that they are looking for is a function of two variables. Okay? It means that the function f depends only of these two real numbers, positive real numbers, which are the distance of x to the origin. Also, they wanted that the function f that they try to find vanishes on the cone. Okay? And so, in the complement of the cone, the function f satisfies this nice equation. These are some properties that they assume to the function in order to find it. Okay? Well, now they define a function f1. F1 is defined in all the R8, although the origin has a singularity, it doesn't matter, but okay, it's defined in all the R8, and is a function that satisfies the same property that they want to impose to f, in the sense that the function f1 depends only of two variables, and also when you change x and y, the function f1 change of sign, and the function is 0 over the cone. Okay. Then they consider the following direct problem. They take any ball into R8 of radius R and consider this derivative problem. The function f is a solution of this equation, and on the boundary is equal always to the function f1. F1 is not changing, the same function everywhere. Okay? And then it has a solution. So they construct a function fr on the ball in such a way that also has the same property that f1 in the boundary. This means that it's invariant under the axiom of this group. And so, in fact, fr depends on the distance of x and y to the origin. Okay, they do that. This is not difficult. The problem comes now, because they now prove the following. You consider two domains, D1 and D2, into R8, which are the complement of the cone. Okay, and intersect this domain. You take the intersection with the ball. Then they prove that f1 is a sub-solution in the first domain and a super solution in the second one. In fact, they produce another function f2, very complicated, which is a super solution in the first domain and a sub-solution in the second domain. Okay, and they use the typical theory of sub and super solution to get the property that I have written here, because this is quite complicated to prove, because they prove that it's a sub-solution on this one, but a super solution is not easy. They need to make many computations, and there appear the dimension. The dimension is not very big, doesn't work. So here in D2, the function f1 is negative. Okay, in D2 is negative. So in all the board you have that the absolute value of F1 is less than or equal to the absolute value of F1. Okay? Now they take limits. They take the sequence of the function fk with k equal to 1, 2, 3, 4, etc. And they prove also easy that this sequence uniformly converges on compact subset of the Euclidean space to an analytical function defined on all arrays. Okay? And then this property keeps in the limits. Okay. They have the solution. The problem is, but this solution is a polynomial degree 1 or not. Then they use this property to prove that it's not a polynomial, because if you take the lim sub of f1 over this constant, this function here, you substitute f1 by this value, and you get that this is equal to the lim sub of this one, which is equal to 1. So, as f1 is less than or equal to f cannot be a polynomial degree. Okay. This is the idea of them, but there are many theories, because it's not difficult. It's very difficult to prove the thing that I have showed you. Okay, this is the idea of Vieri George used it. That in that time was very surprised. Many people were surprised by the result. Well, let me say something about this example, which is interesting in order to know what happened with it. The first thing is that the asymptotic behavior of this graph, they have a very good control of the asymptotic behavior, because in the infinity, the graph is asymptotic to the product of the cone time R. Okay? The cone is in R8, the cone time R is in R9, then they got asymptotic at infinity. This is the first property that you have. The second one is that if you take any isometry of R8, which keep the cone, this means that it induces an isometry of the cone, then the graph has also this isometry. Okay? The same that the function is invariant under this of isometry. It's very nice. The third one is that, of course, they don't construct or not. They construct not only the case for n equal to 4. They construct the case for n equal to bigger than or equal to 4. How? Similar to the other one. They take S here R2n S 2n minus 1, and here okay. They take this sphere here. This is for n at the beginning bigger than or equal to 2, and they consider the Clifford torus in here. And they make the same construction. Okay? But the problem is that when they are trying to prove the property of the graph, they need that the dimension n must be bigger than or equal to 4. So they construct in every Euclidean space of dimension R2n plus 1, they have an entire minimal graph, which is not a hyperplane. And later on, Leon Simon in '89, using the idea of this paper, extended the result to a wide family of graphs. In which sense, instead of to consider this kind of hypersurfaces, they change the Clifford torus for another minimal hypersurfaces, which in particular are isoparametric, principal curvature and constant. Then some of them produce cones which are volume minimizing but not a hyperplane. and with this cone, they produce a sample of entire minimal graph which are not hyperplane. Okay? So there are many samples. This is more or less the history of this result. And now we are going to talk about the stable bursting problem. The bursting problem is closed. Anyway, in the next week, I will give a proof of the result using another technique. But this problem is closed. Then we are going to talk about the stable bursting. The stable bursting problem reduced to this situation. Is any orientable, complete, stable, minimal hypersurfaces a hyperplane for n less than or equal to 7? Because for n bigger than or equal to 8, we know that there are graphs, minimal graph, in particular, there are this kind of example. Well, the solution was given here. All this guy proved in the last 3 years the following, not in the last 3 years, because I am including the case of surfaces, sorry. Then for any n less than or equal to 5, the only solution, the only stable and complete stable minimal hypersurface of Euclidean space are hyper. Okay? The case n equal to 2 were proved by Fischer-Kovic-Schoen, Ogrello, and Tokarmo-Pen. The case n equal to 3, there are 3 different proofs. 2 of them is due to was given by Chodol-Lee, 22-23, and the third one by Catino, Mastroli, and Roncoroni, 23. For n equal to 4, the proof was given by Chodol-Lee, Minter, Stryker in 24 in January, and for n equal to 5, the proof was given by Masset last. Okay? He will talk about the paper on Friday. Well, the problem is what happened with dimension 6 and what happened with dimension 7. Then in the same paper that Bombieri de Giorgi used to construct the graph, they gave another important result, which is this one. They proved that in R8, they can construct an orientable, complete, stable, minimal hypersurfaces, which is not a hyperplane. Of course, if you read the paper, then this kind of word doesn't appear. Complete name is not very usual in that time and so on. But anyway, they proved this. Okay. And now let me also give some idea that how they prove the result. So the open problem, the only open problem is the case of 6-dimensional hypersurfaces in R7. The only. In that case, I believe, but it's only my opinion. I believe that the result is that there are only hyperplanes. There are no another example. Until now, there isn't any proof. Okay. Well, let me explain more or less how they construct this example in the 8-dimensional Euclidean space. They consider again the Simon cone C, and the Simon cone has the complement has 2 components. Okay, and you take one of them in the set, and this component they call E. They call E to the component of the complement of the cone. Then they construct an orientable, embedded, complete minimal hypersurfaces M of dimension 7, which lies in this complement, okay, with the following property. The second one is the more important, because there exists a radius in such a way that outside the ball, the hypersurface is a graph over the cone. Okay? A graph over the cone in the classical sense. You have the normal to the cone, you have the function v, and you go through the normal with v in the direction of the normal. And inside the ball, it's more difficult. So they need to have a good control on the the hypersurfaces inside the ball. This is the idea of them. And also, there is a very nice property, which is the first one. We say that if you take any vector in the component where they define the hypersurface and you take the ray that goes from the origin to D, then this straight line cuts transversally to the hypersurface only one time. Okay? Then as the cut is transversal, then the inner product of the position vector and the normal at that point is not zero. And with the orientability, you can get that is possible. Okay? But this is the support function. The inner product of the position vector time n is a support function. And everybody knows that the support function is a Jacobi function. It's the kernel of the Jacobi operator. So the immersion of this example is stable. Okay? Well, to say that, of course, they constructed this one not only for R8, they constructed this one for any n, in R2n for any n bigger than or equal to 4. And finally, to say that Simon, again, in this case, in collaboration with Hart in '85, using the same idea that before, generalized this example for another hypercomb, different hypercomb. Okay. Well, with this we finish the story or the history more or less of this problem. And so now, during the next day, I am going to prove important properties of the stable minimum, complete stable minimum hypersurface. During the last 40 years, there are many people who have worked on this topic, and there are many results. Try to prove that the only examples are the hypersurface. But I am going to prove here only those results that we need to prove the recent result. Okay? So there are many results that I'm not going to talk about, and I will study the principal property that this kind of hypersurfaces have. Okay. To finish today, let me relate the parabolicity with the stability. Okay. Well, so in a complete Riemannian manifold, everybody knows that a complete Riemannian manifold is called said to be parabolic if you can find a positive superharmonic function, which is sorry, it's parabolic if any superharmonic function which is positive automatically is okay, and is non-parabolic if you can find superharmonic function which are not constant, positive superharmonic function which are not constant. Well, then what happened with the stable minimum complete hypersurface, which is the relationship between this the mathematical object and the parabolicity? Well, the relationship is the following. Result is easy. We say the following. If I take any stable, complete stable minimal hypersurface of the Euclidean space, and I suppose that the metric is parabolic, then automatically the dimension is equal to 2. The surface is a plane. Okay? So, in particular, when n is bigger than or equal than 3, the hypersurface, this kind of hypersurface are non-parabolic. Okay? Well, this is very easy to prove. Let me explain how to prove that. I use again the Fischer-Covey joint result. If our hypersurface is stable, then there exists a positive function on M such that it's a Jacobi function. This is the kernel of the operation. But the Jacobi function is given by Laplacian plus s squared Okay, from here we have that the Laplacian of U is less than or equal to, sorry, is equal to minus the square of the length of the second fundamental form, U. This is positive, this is negative, so this function in particular is superharmonic. Okay? Then it's a superharmonic function and it's positive. Then it's constant. So U is constant. U is constant, the Laplacian vanishes, then you have U square U is equal to 0. This is positive, so you have that the hypersurface is totally geodesic. Okay? Totally geodesic implies a hyperplane. So the manifold and with the used metrics is isometric to an end with the Euclidean. Okay? But everybody knows that the Euclidean metric is parabolic for n equal to 2 and non-parabolic for n bigger than 2. Okay. So n is equal to 2, totally geodesic. Everybody knows that R3, R4, R5 is non-parabolic, as is minus the sample. Well, now I'm going to finish, but before, let me show the next result. The next result is to prove the stable bursting problem for surfaces. I'm going to give the original proof of D'Occam's paint. For me, it's a tribute to Manfredo, because in Granada we have had a very good relationship. He passed away last year. So, and then, in my opinion, it's interesting to give the result here. This result cannot be used in higher dimensions, but be used in a very strong way. And of course, the result that proof is related with the proposition that I have proved here, because we are going to use the uniformization theorem to do this. But anyway, more long. Okay? We will continue with that.
Comments or just because for the stable for entire minimal graphs or large dimension or that are they explicit examples? They explicitly give the function.
It is all the construction that they know. It happens. They are talking solution. They are obtain solution in the both and go to the link. Then you can have some behavior and infinity, some nice properties, but not explicit.
So the example of the minimizing graph that you mentioned, you said when you blow it down, you get R cross C. Right.
But the minimizer graph?
Yeah.
What?
The counter example in dimension 8. It was on the slide a few slides ago. Yeah, that line there, the graph of F has C cross R as N. So that's splitting the line. Is that true for any?
The splitting what line?
The C times R, you always have that structure for the tangent cone sort of that.
Entiendo.
Again, hay una estructura
asíntota a un producto. ¿Tiene que ser siempre asintótico a un producto?
No, no, no.
No, the answer is no.
The only thing is that the entire minimal graph, at least that I know, all of them come from hypercom. All of them. Actually, it's all of them. I believe that for young people, it's better to read the Leon Simon paper than the original one, because he explained on model, with modern techniques, the result.
In the case that we consider the usual triple tolerance in S3, the problem is that it's not, you do the same instruction or the code or the that. The problem is that it's not stable.
Not stable. No, the problem is that the way that they use constructing sub and super solution is you cannot prove that they are sub and super solution for dimension n equal to 2. You have some inequalities and appear n equal to 4. Okay? N less than 4 doesn't.
Can you go back to the slide, the theorem that you're taking?
The Georgie? Ah, okay. No.
Instead of Rm, is it possible to find any ambient space with a matrix that satisfies the theorem? Use that one.
At least I don't know. At this moment, I don't know. The problem is that how can you define the hypercom? Where? So you are working in another different ambient manifold. You have to find what is the substitute of Rm.
Manifold with a whole, I think of.
Yeah, maybe that's. I don't. For me, it's a very, very interesting result. The Fleming one. Many people in that time were surprised by it. And for me, I am studying. For instance, when I will prove next week the reversible result, I will use the integral estimated of Leon Simon showing in the out. It's incredible that you are making many computations at the end appear that H max is possible to pass certain numbers. So how is possible to come? They are making inequalities and many computations, and at the end appear the same.
I mean, none of this, not used, you know. Although that.
This has many influences analysis.
Yeah.
And all the kind of equation.
Okay, let's say
Critica, ¿eh? Critica.
No, no.